3.7. We've essentially talked about it before. It's the geometric character of linear transformations. Matrices are linear transformations. In fact, technically, for those of you that are interested, uh, a matrix is the component expression of a linear transformation. So linear transformations are just like vectors in the sense that they don't naturally have components. Um, the components depend on a choice of coordinate system, in our case, a choice of basis. So until a basis is chosen for a vector space, a linear transformation has no components, if you will. Once, once you choose a basis, then a linear transformation has components and it will look like a matrix. So every linear transformation can be represented as a matrix. In any case, we've already talked about matrices stretching and reflecting things a little bit when we chatted about the determinant. And that's all we're going to do. Less than ideal times, but that's 3.7. I'm not going to ask you any questions about that. 3.8. So we've just discussed linear transformations. They're a special type of function between vector spaces. They're functions that you can pull a constant out of and you can kind of distribute over addition. Now we can combine linear transformations together to make new linear transformations, just like you can combine functions together, multiply them by numbers, you can add or subtract functions, you can do function composition. Same thing here. So if m and n are linear transformations from u to v, then m plus n is also a linear transformation from u to v. And how do we evaluate that? Well, if it's m plus n acting on v, that's the same as m acting on v plus n acting on v. This is just how functions act. So, for example, the derivative ddt and 3 are both linear transformations from f to f, the space of smooth functions. So ddt plus 3 is also. Now, some new notation. We're going to be writing ddt a lot in this chapter and also in the next chapter, which will rely on some of the ideas in this chapter. So I'm going to abbreviate ddt with capital D. So capital D is the linear transformation, the linear operator that takes derivatives of functions and gives you, it takes a function and gives you the derivative of that function. So rewriting this example, d dt plus 3, using this new notation, I'd have capital D plus 3 is a linear transformation from f to f. That reminds me, so just a bit of vocab. If the transformation is mapping a space to itself, so u to u, we call it an operator. If m is linear, then it's a linear operator. So for example, the derivative is a linear operator. All right, so again, we can add linear transformations together and they're still linear. We can scale a linear transformation. So take a linear transformation, multiply by a number, it's still linear. Think about derivatives here. Composition, so kind of important here. If we go from u to v under m, and if n goes from v to w, then you can compose the functions nm. Now, order matters here. So nm would be u to w, because the way it's written, you would do m first, which would bring you from u to v, and then you would do n afterwards, v to w. mn would go the opposite way, would go to w from w to u. And they're not necessarily inverses of each other. It depends. Again, if these are matrices, this is just matrix multiplication. So matrix multiplication is function composition for linear transformations. All right, a bit more about this. So example, capital D, right, that's the derivative. F of r, specifically, these are functions defined on the entire real number line. This E0 is, I've decided to make this a bit more formal. This is that same evaluation of zero function. So it takes a function and it gives you f of 0. So it maps functions to numbers, whatever they are at 0. So then this is a linear transformation. So what does it do? Well, first it takes a derivative and then it plugs in 0. So the effect would be f prime of 0. So this linear transformation would give you the derivative evaluated at 0. Another example, let A for antiderivative sub 0 represent integration where the constant of integration is 0. So it maps smooth functions to smooth functions. Now consider this composition, which is the identity transformation. Right, so the first thing I would do is integrate, and the second thing I would do is differentiate, which is the same thing as doing nothing at all. And in fact, the opposite order is also the same thing as do nothing at all, right? If you differentiate and then you integrate, actually it's not the same, sorry, definitely not the same. Yeah, so think about why it's not the same in reverse. So we're multiplying things together here, we're composing, and so this issue of commuting comes up, the commutative property. So let's do some examples in the context of derivatives. So take two linear transformations, linear operators, d plus 1 and d minus 1. Remember, capital D is the derivative. Consider m times n. So I can multiply these out as if I was doing ordinary algebra. I can simplify and I get d squared minus 1. This is a new linear operator. And you can apply it to a function. And what would you get? Well, you'd get, so d squared on the function is two derivatives, and minus 1 is just multiplying by 1. So I get f double prime minus f. Now, let's compare this to something that seems like it ought to be the same. D minus t and d plus t, where t is the variable here. So these derivatives are d dt. Let's multiply s by t. Be very careful here, because d is not a variable. This is not like the letter x. You can't plug in numbers for d. Right? It's a linear transformation. So if I multiply d times d, I get d squared. D times minus t, the order is very important here. I'll talk about it in a second. Then plus t times d, and then plus t times minus t. So minus dt is not the same as minus td. So why not? Well, these are all transformations. So let's try it out. If I take minus dt and I apply it to f, what do I have here? I have the derivative of t times f. Well, that's a product rule, right? F prime plus 1 times f. If I take minus td times f, that's just the derivative of f times t. This is very new because we're doing something, we're foiling, which we've done a bazillion times before. But now we're doing it with linear transformations, and we have to be careful. So we can't, up here, it was fine. D times minus 1, you can pull the minus 1 right through. Constants go through linear transformations. Functions do not. So these two don't commute. The order of operation matters. The order of multiplication matters. All right, we'll pause here.